Before we start looking, this is video for section 6.2, the natural base E. Before we start looking at this weird thing that's E, we're going to walk through and look at the exploration a bit. Okay, for exploration 1, excuse me, it asks you to take 1 and then add 1 over 1 and then add 1 over 1 times 2. 1 over 1 times 2 times 3, and notice what happens. So we're going to go ahead and keep doing that. I'm going to use Desmos to do that because it I can add on to an expression really easily. I just type the 1 and then the backslash divide by button. 1, and to get the times, that's a little star or shift 8 times 2 times 3 times 4 times 5, and what do I get? 2.7166. If I add another 1 divided by 1 times 2 times 3 times 4 times 5 times 6, okay, we end up with 2.718, okay. Now if we keep going, 1 divided by 1 times 2 times 3 times 4 times 5 times 6, I did an exponent instead, times 6 times 7, okay, 2.7182, and if we keep on going, we notice is we actually 5, 6, 7, 8, okay, 2.7182. We actually keep getting closer and closer. We used to take this out for a really long time. 1 divided by 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. 2.7182. If you notice, we actually stopped, the numbers kind of stopped changing. Just these last numbers of this decimal change. What we're actually approaching is this number, is 2.718279 ... It's irrational, kind of a lot like pi. Hey, but as I'm adding these smaller and smaller and smaller fractions, these fractions keep getting smaller because the decimals keep getting bigger, we approach this number 2.7182. Okay, and they notice that, so instead of just referring to this number all the time as 2.718279, we decided, okay, let's just give it a name. Let's call it E. Okay, so we started calling this number E. Okay. So that's one way of finding the number E. One other way is to look at the function of our exponential model for exponential growth. And if our growth rate, here our R, and our time x are the same, we end up getting a curve over here that looks kind of like this. Okay. But what's interesting, as I trace along this curve, as I keep tracing out, we get 2.5, 2.57, 2.618. If I keep tracing it out, it looks like it flattens out, but it never actually completely flattens out. And if I evaluate this for extremely large numbers, if I figure out what f of 100 is, it's 2.714. F of, one nice thing about Desmos, makes it very easy to plug stuff into a function. F of 1,000. F of, let's do scientific notation, let's go 10 to the 5th, 2.7182. If you notice, it's approaching the same number up here. We're approaching E. So that is what the number E is. The number E is approximately 2.7182. Okay, and we get there, again, there's two different ways of showing how we get there to that E value. Okay. Okay, so as you saw on Desmos, the number E, okay, is just a number. E is a number. Okay. Again, this was another special number that we noticed. It correlates to, the best definition for it is if I look at the equation, y equals 1 plus 1 over x to the x. As x gets really big, as x approaches infinity, as it gets really, really big, this expression approaches this number E, which we approximate as 2.718281 dot, dot, dot. It looks like it repeats, but it doesn't. It's a non-repeating, non-repeating, non-terminating decimal, so that does make it irrational. Other famous irrational numbers that we know, for example, are the number pi, the square root of 2. Those are all irrational. So e is just an irrational number along those same lines. Okay, so we treat it the same way we would treat a pi, or we would treat the square root of 2. Okay, so our same exponent rules apply, our same function rules apply. It's just a number that we use for our base. We call it the natural base. Okay, it occurs in a lot of natural settings, such as certain exponential growth in populations, whether animal or people, cells, so forth and so on. So hence why we call it the natural base. It's our natural base E. And this number was just discovered by looking at patterns and noticing a pattern here that this number always, that certain things always approach this 2.7182 number. Okay, so we treat it in much the same way, again, not much, exactly the same way as we treat any other type of base. Again, we use it as a base of an exponent. Okay, so if I have e to the third times e to the sixth, we treat it like any other type of base. If this is 2 to the third times 2 to the sixth, we would add our exponents and we would get e to the ninth. Same thing, e to the ninth. Okay, again, we would treat it like we treat any other base. If this was 2 to the fifth or x to the fifth and x to the fourth, we would take the 16 divided by 4, which is 4, and then we would subtract my exponents when I'm dividing. 5 minus 4 is 1, so this should just be 4e. Okay. Again, my same exponent rules apply here. So if I have 3e to the negative 4x, this exponent on the outside applies to both pieces, so it would be 3 to the second, e to the negative 4x to the second. So this exponent applies to both pieces, the 3 as my base and the e as my base. 3 to the second is 9. E to the negative 4x to the second, a power to a power. We have to remember those exponent rules. Those multiply. So it'd be e to the negative 8x. Okay, but again, our rules of negative exponents still apply. So this is going to take the reciprocal of the e. So I'd have, this would be the same as 9 times 1 over e to the 8x, which we tend to write as 9 over e to the 8x. Okay. Okay. So let's go ahead and let's just look at what the graph of these, of a exponential equation with a base of e would look like. Again, it's the same rule as our last section as far as exponential growth, exponential decay, except our base is always e, so we can't determine that growth based on the e. But here, if I just have the equation y equals e to the x, here I have a base of e. Again, e is greater than 1. E is greater than 1, so that tells me it's going to be an exponential growth. Again, a growth, so it would be e to the x. Okay, and again, we still have that growth pattern where it goes through the point 0, 1, because again, e to the 0 is 1. Anything to the 0 is 1. Okay. But then e to the 1, well, we know that's approximately 2.7182. So that means when I put a 1, I'd have the order pair 1, 2.7182. Okay. All right, to show exponential decay with a base of e, since e is greater than 1, we do e to the negative x. Again, that's just the reciprocal. Y equals e to the negative x is the same as saying 1 over e to the x. Okay, which then we could rewrite, well, 1 to the x is just 1, so we could write it like this. So now my base is less than 1, which corresponds to my decay function. Okay. Again, when I put a 0 in, we get 1, so we have the point 0, 1. But now it's slightly different in that the fact that when I put a 1 into this, I get a negative e, so when I put a 1 in, I get negative 2.71. So this point here corresponds to the point 1, negative 1, 2.718. is that point right there. Okay. And then when I put a positive 1 in, I just get the reciprocal of E, which would be 1 over 2.718. That's where this part comes from. Is the same as 0.368. But again, there's nothing new here. The only thing that changes is our base isn't just any random base. Our base is E, this number E, 2.718. Okay, so let's go ahead and let's look at some functions. There's a typo in my notes. Let's go ahead and let's adjust this typo. This should be 3e to the x. Okay, so it should be y equals 3e to the x. So if we look at that function, if we want to graph it, okay, we can go ahead and plot some points, figure out what happens when I put certain things in. So we could create an XY table. I think we're going to go ahead and look at Desmos and get the graph from that. We're looking at the function y equals 3e to the x. I'm not seeing anything, but look, my window's way over. So let's move over. There we go. Okay, so we have 3e to the x. Okay, so as we look along this function, if we see here it goes to the point 0.03, because when I put a 0 into this, if we write this as function notation instead, okay, it makes it much easier to type in a value. So when I put in a 0, we get out a 3. Okay, when I put in a 1, f of 1, I get out 0.815, because that's taking that pi, taking that e and multiplying it by 3. Okay, so here I have the 0.03, okay, and we can go ahead and trace along here, plot a few points to get an idea on what this graph looks like. Okay, another way is we can actually create a table. Let's see if I can do this. Here if I type f of x1, no, that's not going to work. Oh, yeah, well, if I start putting numbers in, a 0, a 3. Now I can just type in a 1, and that's what it gives me. And look, it plots my points over here as I put them in the table. So the point 2 is way up there at 22. Okay, let's go ahead and let's put some negatives in. Negative 1. We get -2, -3. So that we can go ahead and plot these points on our paper and connect the dots. So go ahead, plot those points on your notes, connect the dots to create that smooth curve. Okay. Now let's also look at example 2 part B. Okay. From our notes we're given the function f of x equals e to the, to get the exponent button, it's just shift 6, it's the up caret, -0.5x. So since I have a negative up here in my exponent, that tells me it's going to be an exponential decay function. Again, I can create that table, this plus sign, add table, and I don't want y1, I want f of x1. Now I can plug in a 1, we get 0.606, plug in a 0, we get 1, plug in a 2, 3, how about a -1, -2, -3. So there I have my points, plot my points on my graph and connect it with the smooth curve. All right, now to see a purpose or a use for this miraculous number e. Hey, if we remember our compound interest problem that we did earlier, we had this compound interest equation. We had a equals p is our principal, 1 plus r over n to the nt. Again, where p was our principal, r was our rate, and n here was the number of times compounded. But if you look at this, the number of times compounded, if we look at this n, as n gets really big, this n gets really big. And if you notice, it looks a lot like this, 1 plus 1 over x to the x. We have 1 plus r over n to the nt. Okay, so as this gets really big, it actually approaches the number t. So as the number of times you compound it, if you compound it 4 times a year, that's quarterly. If you compound it daily, 365 times a year. If you compound it every hour, every minute, every second, every moment, as that e gets bigger and bigger and bigger and bigger, we approach our continuously compounded interest, where the interest is continuously compounded and added on, okay? And we end up getting then this equation, A equals P. This approaches E, so we'll have E to the exponent of RT. Again, where R is your interest rate, T is your time in years. So R here is your rate, T here is the time in years. Okay, and again, P is still your principal, your original amount invested. Okay. Principal, your original amount invested. Again, E is just that number, E, RT. I always remember it as PERT, PERT for continuously compounded interest. Okay, this is a much easier equation than our just compound interest equation, but this is if interest is compounded continuously. Okay, so let's go ahead and let's look at an example here. You and your friend each have accounts that earn annual interest compounded continuously. So it's compounded all the time, continuously all the time. The balance A in dollars of your account after 2 years can be modeled by this equation. So if we see here, this is you, and then over here we'll go ahead and we'll talk about your friend, because we have a friend also. It says the graph shows the balance of your friend's account over time. So this is the graph of your friend's balance. Here's the equation of yours. So your equation is 4,500 E to the 0.04T. So I can tell from that my original amount, my original principal is $4,500. So this is my principal. And my interest rate, and there's my rate, 0.04, so 4%. My rate is 4%. Okay. Which account has the greater principal and which has a greater balance after 10 years? Okay. So we're trying to figure out which one has a greater balance after 10 years and which has the greatest principal. Well, we know our principal is 4,500. Okay. The principal, again, is the amount of money you start with. So let's go ahead and let's look at your friends and let's see, according to this graph, how much money did they start with? Well, at 0 time, at 0 years, they had $4,000. At 0 years here, if my T was 0 here, this would be 1, so it would be $4,500. So I can tell from your graph that your friend's principal is $4,000. So which account has a greater principal? Yours did, an extra $500. So, so how would we say that? My account has the greater principal. $4,500. Okay, and they have 4,000. Okay, which has a greater balance after 10 years? So this is my T. If T was 10, who's going to have the most money? Well, I could find what T is when T is 10. Okay, for my account. So I'm just going to figure out when T is 10. So for our accounts, we have 4,500 E to the 0.04 times 10. There's actually an E button in your calculator. Okay, the E button in your calculator is located right here. They're a little blue. And since it's used so often as a base, it's even an E to the X, so it's automatically an exponent. So if we have 4,500 times E, so to get to there I'd have to go second, that button, E to that, and then 0.04 times 10. So I would have a balance of $6,713.21. So that's me. Now let's go ahead and let's look at our friend. I don't have the equation for my friend. I don't know their interest rate, but I do have the graph. And we want to know at 10 years, so here at 10 years, so 4, 2, 4, 6, 8, 10 years would be right here. So I can look straight up and see what do they have here. Well, this is 6,000, this is 7,000. They have more than $7,000. You only have 6,713. So your friend has a greater balance. So we would say my friend has a greater balance after 10 years. How is that possible, that your friend has a greater balance, but you started out investing more money? I started out investing $500 more than my friend, but yet after 10 years they have more money. I want you to go ahead and jot down some reasons on why. Or how is that possible that your friend could have a greater balance? Okay. So if you have any questions, bring them to class for us to discuss. Hey, and good luck.